In Chapter 2, we looked at the diffusion equation. Here's the one-dimensional version of that. This is the diffusion coefficient, so this is the diffusion term. Then we had a convection term where you have a wind or current velocity v, and then there were source terms or reaction terms also. Now in Chapter 3, we're going to study two very different looking problems that have some similar characteristics. One of the problems is simply going to be the convection problem without diffusion. In other words, we assume that D is 0 or negligibly small, so there's no diffusion, only convection and possibly reaction source sink terms. So we're going to assume that D is 0 in this equation, and that changes the nature of the equation dramatically. Now it's first order in T and first order in U. So here's the convection problem, or transport problem. There's no longer any diffusion. That changes the nature of the problem. Physically, it's obvious how it changes it because diffusion has a smoothing effect. With diffusion, the solution is always smooth. Without diffusion, it's not necessarily smooth. We just have a convecting current or wind, and the solution, if it's initially discontinuous or poorly behaved, it may continue to be poorly behaved, so it may be a more difficult problem without the diffusion term. Now we're going to assume for the moment that V is positive. That means the wind is from left to right, and therefore physically you have to have a boundary condition only on the left-hand side. See, now you have the previous problem we had was first order in time and second order in space. So we had two boundary conditions in space and just one initial condition. Now we still have one initial condition, but it's only first order in space, so we should only have one boundary condition, and that should be at the left-hand side if V is positive, because you want the boundary condition obviously to be upwind. You need to know the temperature or concentration of the diffusing element at the point where it's entering the region, not at the point where it's leaving. So we're assuming V is positive, which means the wind is from left to right, therefore the boundary condition should be given on the left-hand side. If it's not, the differential equation with boundary condition is simply not well defined. So now we have several options for how to approximate the terms, the derivatives in this transport or convection equation. Perhaps the most obvious would seem to be use Euler's method on the time derivative, as we always have, u tk plus 1 minus u at tk over dt. The question is, how do we approximate the space derivative u sub x? We could use a centered approximation, that is u of xi plus 1 minus u of xi minus 1 over delta x. That's one possibility. Another possibility would be what's called an upwind approximation, where we approximate still the time derivative the same way, the Euler approximation as always. The space derivative, though, we could approximate by u xi minus u xi minus 1. That's called the upwind difference method. Or we could even have a downwind difference, which would be shown here. Now we're approximating the space derivative u sub x by u of xi plus 1 minus u of xi over delta x. Now there's an obvious problem with the downwind difference that causes us to discard it immediately. If you look at how you would use this method, it tells you how to calculate this value from these two, this value from these two, this value from these two. It doesn't tell you how to calculate this. It tells you how to calculate this from these two values, but that's a boundary condition, so it's either going to agree with the boundary condition, in which case it's redundant, or it's going to disagree, in which case we have a contradiction. So this downwind difference method is clearly not a reasonable method. In fact, if we do a Fourier stability analysis, we can show that it's unconditionally unstable. Another reason why it doesn't make any sense physically is you're trying to predict, it's like you have a wind coming from the left, and you're trying to predict the future temperature based on the temperature downwind. Well, if you want to predict the temperature, you want to know what's the temperature like upwind, not downwind. So it doesn't make any sense, and it seems reasonable to be unstable. If we do a Fourier stability analysis, as is done in Appendix B, of the centered difference stencil, we will find that it's also unconditionally unstable, so it's no good either. So we're going to concentrate on the upwind difference method, which makes sense physically. We're trying to predict the temperature here at future time based on the temperature here and upwind. That makes a lot more sense, and as far as the calculations, it makes sense also because we're calculating this value based on these two, this based on these two, this based on these two, this based on these two, and we can't calculate that, but we don't need to. That's given as boundary conditions, so we're able to calculate everything on the first row and then the second row and so forth. So it makes sense, but it's still not obvious that it's stable. The time-dependent problems, finite difference methods, it's awfully hard to predict stability until you actually do the analysis. There are methods that seem perfectly reasonable that are totally useless. The centered difference methods seemed sort of reasonable, but it's totally worthless. First, let's look at the truncation error. And the truncation error, again, I'm not doing the detailed calculation, but it's pretty simple. And it's exactly what you would expect because you're basically using an Euler approximation to u sub t and an Euler approximation to u sub x. They're both first order, so the truncation errors order delta t and delta x, first order in time and space, so not terribly accurate. Okay, so now let's do the Fourier stability analysis on the upwind explicit approximation to the transport equation. As usual, we leave off the lower order terms because they never affect stability and just look at the highest order term in time and the highest order term in x. And we'll assume v is constant and positive so that the wind is coming from left to right and boundary conditions are given on the left. Then the explicit upwind approximation is this, u at tk plus 1 minus u tk, both at xi over delta t. And see this upwind because we're taking u at xi minus u at xi minus 1 to approximate the space derivative. And as we learned in Chapter 2, the Fourier stability analysis consists of simply replacing u of xi tk by a of tk e of I m xi. In other words, we actually expand u, the approximate solution, in a Fourier series where the coefficients vary with time, a discrete Fourier series. The coefficients vary with time. We want to see what happens to a typical coefficient a sub m as time goes on. Does it grow exponentially or not? So we plug in a of tk e of I m xi, and this is at tk plus 1 xi. This is tk xi, tk xi, tk xi minus 1, tk xi minus 1, and we factor out the e to the im xi. On the left hand side, factor out the am of tk because both of these are at the k level. And as always, we divide through by e to the im xi, so this term disappears. That becomes a 1. This disappears and you get e to the minus im delta x. So after dividing through by e to the im xi, as we always do, we get the following. Now I'm multiplying through by delta t and defining r to be v delta t over delta x. We're assuming v is positive, so that's greater than or equal to 0. It's positive. And the characteristic polynomial then, see this is your lambda term and these two are the constant terms. So as in the usual stability analysis, we approximate a of tk by lambda to the k, and we get characteristic first order characteristic polynomial because it's a first order recurrence relation. For fixed m, it's just a homogeneous constant coefficient linear recurrence relation, first order. There it is, and the root, one root is 1 minus r plus r e to the minus I m delta x. So the question is, are is this less than or equal to 1 an absolute value for all m? If so, it's stable. If it's ever bigger than 1 for any m in absolute value, then it's unstable. Well, you could do a little more direct analysis of the absolute value of lambda here, but the simplest way is to look at this in terms of the complex plane. Say lambda can be complex here, I being the square root of minus 1. This e to the I times real number, remember, is always a complex number of absolute value 1. So as m goes from 1 to n, lambda traces out a circle of center on the real line at the point 1 minus r and radius r, because this e to the I theta term is always has absolute value 1. So lambda is always distance r from the center 1 minus r. So for all m, lambda lies on a circle with center at 1 minus r and radius r in the complex plane. If you think about that, that's a circle that lies entirely inside the complex circle lambda, absolute value lambda equal to 1, if and only if r is less than 1. That is, if the radius of that circle is less than 1. This is a circle that for any r between 0 and 1 lies entirely inside the unit complex circle. If r is bigger than 1, then the center, well, the radius is bigger than 1, so it obviously can't be inside the complex circle of radius 1. So r needs to be less than or equal 1 for stability, and looking at the definition of r, which is v delta t over delta x, that has to be less than or equal to 1, means delta t has to be less than or equal to delta x over v. So this method is conditionally stable, that is, it's stable if and only if delta t is less than or equal to delta x over v. So it's the other two methods, the downwind and centered difference methods, were always unstable. The upwind method, explicit upwind method, is at least stable if delta t is smaller than delta x over v, but it's even the upwind method is unstable if delta t is larger than that. In Appendix B, several finite difference methods are analyzed using the Fourier stability method. This is the characteristic polynomial for the upwind explicit method, the one we just got through. Here's the characteristic polynomial of degree 1. There's the condition for stability. This one is for the centered difference. The other page we can't see here, but it's the centered difference method, explicit centered difference method, and as I said, that's always unstable. The downwind method is always unstable also. As an example on page 101, u sub t equals 2ux. Notice here v is negative 2, so that means the wind is actually from right to left, which means the boundary conditions had better be specified on the right end, and they are. And we use the explicit upwind method that we were just talking about, and here are the results. V is 2 here, so delta x over 2 is 0.01, and we see, in fact, if delta t is less than delta x over v, as it is here, everything's fine. If it's slightly greater, it does indeed become unstable. Now there's an interesting nonlinear transport equation on page 105 that illustrates how difficult these first order equations can be. It's nonlinear because you see the velocity is dependent on the solution, and you see that v is actually, the velocity is minus u. We actually have boundary conditions at both ends. Why? Well, the initial conditions are u equals x, which means that x equals minus 1, u is minus 1, which means v is plus 1, so the wind is into the region from the left-hand side. Over here, v is, from the initial conditions, since v is minus u, The left-hand side, V is positive, which means the wind is into the region. At the right-hand side, V is negative, which means V is into the region from the right-hand side, so you need boundary conditions on both sides. And in fact, basically, you can think of this as a tube where the wind is blowing in from both sides. However, one side, the wind is cold, and the right-hand side, the wind is hot, and they're blowing toward each other, and they meet in the middle, and after a certain amount of time, they meet, and there's a sudden discontinuity in the solution where the hot and cold winds meet in the middle, and the solution is simply undefined after that. There's a shock wave, and it doesn't matter what method you use, finite difference, finite element, no matter how small step sizes you use, you won't get good solutions past t equals 1 because the partial differential equation itself blows up there. And this happens in a lot of complicated nonlinear first order equations. The solution can simply become unstable and blow up. Okay, the second part of chapter 3 looks at another equation. This is a wave equation. It's actually second order in time and second order in space. It represents, for example, a vibrating string where u is the height of the string at time t and at point x on the string. This could be a source term here. We'll mainly be assuming f is 0. So, and c turns out to be the velocity of the wave. It's a second order in space and time. So as you would expect, we need two boundary conditions in space and two initial conditions, namely that u is given for all x at t equals 0 and u sub t is given. Second order in time, so we need u and u sub t given. Okay, well, the obvious, there are a number of possible finite difference approximations to this equation as usual. The most obvious one would probably be the centered explicit method where you approximate utt by this. U at tk plus 1 minus 2u tk plus u tk minus 1 over delta t squared. And similarly, you approximate u sub xx by the usual second order difference approximation at tk. So you could approximate the right hand side at tk plus 1 or tk minus 1, but it seems reasonable to center it and evaluate tk. So here's our stencil for the wave equation for the explicit centered difference method. We approximate utt by this minus 2 times that plus that over delta t squared. Approximate uxx by this minus 2 times that plus that over delta x squared. And it's a three-level scheme. That is, to calculate u at the level tk plus 1, we need to know it at the two previous levels. Well, the initial conditions tell us the values at t equals 0, but we need to know the values at the first level also at t equals dt, delta t. And how do we approximate that? Well, the simplest and most obvious would just be basically Euler approximation. You essentially use Euler's method, the first step. This is u at 0 plus delta t times ut at t equals 0. That would seem to be, those two terms would seem to be a good approximation to u at this level. Turns out that that's not accurate enough. It'll still converge if you use that, but you need to use another term in the Taylor series, otherwise it won't be a second order accurate. The truncation error, as you would expect, is second order in time and space, that is proportional to delta t squared and delta x squared, because we're using the usual second order approximations to the second derivatives. So you would hope this method would be second order in space and time. The truncation error is. However, if you don't use the extra term in the Taylor series for approximating u on the first level, you ruin the scheme. Is only going to be order delta t. Well, since we've seen that reasonable looking finite difference schemes can be totally unstable, let's check the centered explicit approximation to the wave equation. Again, only look at the highest order terms because the lower order terms don't matter for stability. And here's our centered explicit finite difference approximation. The right hand side is all at tk, left hand side's at xi, and as usual we substitute one term in the Fourier series for u a of tk e to the I m xi here, and these are all at xi, the left-hand side, and tk plus 1 minus 2tk, tk plus 1, and the right-hand side we have am of tk in all three terms because they're all at tk, and we have xi plus 1, xi minus 1. Now the left-hand side we can factor out the e to the I m xi, and the right-hand side we can factor out the am of tk because they all have am of tk in them. And as always, we divide through by e to the I m xi to get rid of the xi's. And left-hand side is this. Right-hand side, the usual, the xi disappears here, and you get e to the I m delta x minus 2 plus e to the minus I m delta x, the usual approximation. And as we saw in chapter 2, we can replace this by using some trig identities, Euler's formula plus a half-angle formula. And this numerator here is simply minus 4 sine square of m delta x over 2. That's a formula that you're going to need every time you use the Fourier method if there's a second derivative there somewhere. And so we multiply by delta t squared, and we have c squared delta t squared over delta x squared times minus 4 sine squared. And I'm going to combine the c squared, the delta t squared, the delta x squared, and the sine squared all into one term. I'm going to call it r. Notice that r is always greater than or equal to 0. So the right-hand side just becomes minus 4r times am of tk. And take this on the left-hand side, it combines with the am of tk here, and we have a minus 2 plus 4r in the characteristic equation is the multiple of lambda. So our characteristic equation is a lambda square and then a minus 2 plus 4r lambda and a 1 for this. So there's our characteristic equation. Now notice this is a second order. It's a quadratic polynomial. So we have to look at both roots. And for stability, both roots for all m have to be less than or equal to 1. So what are the roots of this quadratic? Well, you can simply plug into the quadratic equation and do some algebra, and you'll come to the same conclusion that I'm going to conclude here. But a little simplest way of doing this is to notice that whether the roots are complex or not, their product is always 1. Why? Because this can be factored as lambda minus lambda 1 times lambda minus lambda 2. Multiply that out and you get lambda 1 times lambda 2 has to be the constant term 1. So the product of the two roots is always 1 regardless. So we take two cases. If the discriminant, which is b squared minus 4ac, which comes out to 16r times r minus 1, if this discriminant is positive, that means you have two real roots whose product is 1, and two different real roots. If they're different, one of them has to have absolute value greater than 1, one of them has to have absolute value less than 1. The fact that one has absolute value greater than 1 means the thing is unstable. So if the discriminant is positive, it's unstable. If the discriminant is negative, then you have two complex roots. They're complex conjugates. Their product is also 1. That means they both have the same absolute value because they're conjugates, and that absolute value must be 1. So both roots have absolute value equal to 1, and it's stable. So it's going to be stable if, for all m, the discriminant is negative. Well, the discriminant r, remember, is greater or equal to 0, so the only way this could be negative is r is less than 1. So if r is less than 1, the discriminant is negative, and you have two complex conjugate roots, both of absolute value 1. So if r is less than or equal to 1 for all m, then all roots will be less than or equal to 1 for all m, and it's stable. Well, here, remember what r is. It's got an m in it, but sine square can never be greater than 1. So if this part of r is less than or equal to 1, then no matter what m is, the whole thing is less than or equal to 1. So it's stable if this is less than or equal to 1, which means delta t is less than or equal to delta x over c. So that's the criteria for stability here. So again, it's conditionally stable. The explicit centered finite difference method for the wave equation is stable provided that delta t satisfies some has to be less than this threshold, delta x over c. In Appendix B, here is the characteristic equation for the centered explicit finite difference method. This is the one we just analyzed. There's your lambda square minus 2 plus 4r. R is this thing here. And as we just concluded, delta t has to be less than or equal to delta x over c for stability. Okay, we conclude with an example. This is a wave equation. It's a damped wave equation because of the ut in here. The first order time derivative here, it's a damped equation, and notice it's a two-dimensional problem, and in fact the region is a triangle, sides 1, and we have u equals 0 in the entire boundary, and at t equals 0 u is given and u sub t is given, and basically we have a wave equation. It's second order, it's a two-dimensional wave equation, but we can do a Fourier stability analysis similar to what we just did for the one-dimensional case and come up with a similar criteria for stability for the explicit centered finite difference method. Here is the explicit centered finite difference method applied to this two-dimensional problem. Now u is a function of x, y, and t, and the left-hand side, the ut, the second derivative with respect to t is approximated as usual by u at tk plus 1 minus 2u at tk plus u at tk minus 1 over delta t squared. Here's the approximation to the u sub t, which doesn't matter as far as stability is concerned. Here's the usual centered explicit approximation to uxx, uyy, and here's the program. Pretty simple. There's the entire program. Because it's explicit, there are implicit methods for the wave equation, by the way, that are always stable, but then you have to solve a linear system every step. This is explicit, so you can solve for u at xi, yj, tk plus 1 in terms of things at the tk and tk minus 1 level. The uk is the tk level, ukm1 is the tk minus 1 level. So here's the main loop here that it calculates the value of u at xi, yj at tk plus 1 in terms of values at tk and tk minus 1. That's all there is to the program. And if you violate the stability criteria for this two-dimensional problem, in fact it does blow up. Notice in this problem we're solving the problem in a triangle. Its finite difference methods are rather problematic for complicated two-dimensional or three-dimensional regions. That's the main advantage of finite element method, which we'll study in Chapter 5. So if we have complicated regions, you should normally use the finite element method. Finite difference method is easy to use if the region is a rectangle, or here this is not a rectangle, but it's still pretty easy to use, but you have to be careful that the grid points lie on the boundary, otherwise it complicates things. So we'll normally just use finite difference methods in rectangles or real simple regions. For more complicated regions, we need to use the finite element method.